The motivation for this class of matrices I'm going to spend the next few weeks talking about is pretty straightforward. In 2015, we have very large matrices, and we want to be able to do things on them very, very quickly. And while we've learned in classes like CS515, there are these wonderful, robust algorithms like SuperLU for a system, or Wilkinson QR for eigenvalues, or Golub-Kahan for SVD, and those work for all matrices. They are n-cubed, which makes them completely infeasible for bigger systems. So we turn to how can we find broad classes of matrices that appear in lots of applications, but for anything in that class, we can find really, really fast algorithms. And the one you're probably the most familiar with, the one they talk about at the end of CS515, is sparse matrices. Lots of great algorithms for that. The next most common one, which is my research area, which I find is not talked about a lot in classes, are rank structured algorithms. So this is a very large class of matrices you'll see in applications that admit ON linear time algorithms. Okay, so this week what I'm going to talk about, I'm first going to discuss the history, how rank structured matrices, where they kind of started from, and kind of the progression they've taken over the past. It's a relatively new field, but over the past 20 years or so, the development. Then I will spend some time on H matrices, which I will preface right away is already an outdated form. But you will see them, they are extremely important in terms of the theory, and I think they are a lot more easy to understand than some of the more complicated rank structured forms that we use in a research today. So that's kind of how I'm going to introduce the idea of a rank structured matrix, and they really do play a very important role in the history. In that sense, I will also review the singular value decomposition, which I know you're all familiar with, but it plays, especially theoretically, a crucially important role in rank structure. So I'll make sure we're all on the same page in how I'm going to utilize that. And as an example, just to very concretely show you how we take advantage of the rank structure to get a faster algorithm than we otherwise would have for a non-sparse, for a dense matrix, I'll go over what an H matrix vector product looks like. Then I'll move quickly to SSS, sequentially semi-separable matrices. These are also outdated, and they're also not so easy to understand. So that's going to be a very quick slide. But they're worth discussing because you will see them in literature, and they are the direct descendant of HSS, which in my opinion is the current state of the art in terms of rank structured matrices. Then we'll talk about HSS, H squared, and HBS matrices, which you'll be happy to hear are all more or less the same thing. So only one difficult definition to understand, but we will build up that definition very carefully over the course of 20 minutes to make sure you understand what exactly these matrices are coming from. Then I'll give a couple examples of HSS matrices you might have seen already in your research that you may not realize had this nice property. I'll talk about the interpretive decomposition, which is, in a few words, kind of how we do the SVD in practice, just kind of a faster way that gives us really the same information the algorithms use. It's very important. And then I'll briefly touch upon how you get the HSS form, basically linear storage for a quadratic matrix of dense numbers, from that dense matrix, and how you do that. I don't find this algorithm learning about it very constructive, but I think it's important that you see it at least a little bit. And at any time, if there's anything that's in either my notation or is unclear, anything you want to ask me more about, please stop me at any time. But yeah, this will be the plan for today. And then next week and the week after, we'll get into some really fun stuff and how you can solve linear systems and eigenvalue problems at HSS really fast using a lot of cool linear algebra tricks. Okay, so our story starts in 1999 with Wolfgang Hackbusch, who a lot of you may know of as the inventor of multigrid methods. Very big name at the University of Kiel over in Germany. And I will define these matrices very carefully over the next few slides, but it's really, if you have a good understanding of multigrid, it's really the same idea except for the off-diagonal blocks are going to have a low rank property, which you wouldn't necessarily have in just a general multigrid process. So I will talk about that a lot more in just a minute, but yeah, I will utilize, they're no longer very practical, but they really get at the heart of what rank structured matrices are without convoluting the definition. The next thing to come up was SSS matrices. And this was introduced by Shivkaran Chandrasekaran, actually an electrical engineer at UC Santa Barbara, and Ming Gu, who's my grand advisor at UC Berkeley. And I won't spend a lot of time on this definition because it's outdated and convoluted, but it was a really important step because this is when they realized that hierarchical matrices, instead of just having properties, something called a nested basis, which I will talk a lot about in just a few minutes, but it was key in terms of getting linear complexity. You needed to have this nesting. And Sss matrices were the first ones to do it. They did it in the wrong way, but they're the first ones that did it. And that was a huge step in terms of the process. Yeah, so it is a special case of H matrices that allow for very fast algorithms that come up a lot in electrical engineering. Okay, so now let's talk about H matrices. So we start our story with the SVD, which I'm sure you guys are all very familiar with. So any m by n matrix, not assume any rank properties, square, symmetric, anything about it, emit a factorization like this, where we have on the left and the right, we have our singular vectors, where left singular vectors are just the eigenvectors of A transpose, and our right singular vectors are just the eigenvectors of A transpose A. And the singular values in the diagonal of the diagonal matrix are the eigenvalues of both AAT and ATA, which, as you know, descend and really show the spectrum. It showed in a decreasing order keeps all the information. And there's this famous theorem called the Young Theorem, which I will talk a little more about in a few minutes, that says in a very precise sense, if we want to keep the best rank 5 approximation of a matrix, the best rank 10 approximation of a matrix, the way to do this is by keeping 10 singular values, 5 singular values. Now in practice, it's not always worth it to compute the singular value decomposition to do all that work. We instead do something called the interpolative decomposition. But at least in a theoretical sense, this is always what we want to do in a rank approximation. Now something I would like to note here is the SVD in terms of a tolerance, which means now maybe you have for a 10,000 by 10,000 matrix, 10,000 non-zero singular values, but let's say after 20 of them, they're all 10 to the negative 13 or smaller. And they're really not adding anything to the matrix. And this happens all the time in applications because things like noise in the data or just, smooth, it can be a lot of things that can make this. And then you're just really wasting valuable storage and everything keeping those. So that's really a fundamental idea here is we take an SVD and we cut it off not when they're non-zeros, but just when they're small numbers. So this is called the numerical rank, and it will come up a lot, of course, in this talk. Yeah, so this is mostly stuff you guys have already seen. So let's take an H matrix. It looks like this. You just divide it up, and take off-diagonal blocks that are smaller and smaller near the diagonal. And all we ask is that for the blocks I've covered blue, every block except for the ones right in the diagonal, the rank numerically is k or smaller, where k is some number that's very small compared to the size of the matrix. In practice, we want k to be at the very most log n. Otherwise, it's not worth it to form this H matrix structure. There's something I can prove for you if you want to see. And then what we can see here is that if we were to do, say, a matvec, it's a pretty easy complexity calculation. Instead of n squared, we just do these block by block, the kind of thing we see in CS 515, and it is n log n. Now let's be a little more explicit about that to kind of illustrate how we use this structure. And the first step is by forming a tree structure, which is very fundamental to this field. H matrices a lot of times used to be referred to as tree codes back in the 2000s because people had to learn all these how to program binary trees and use them. And the idea here is we split up our matrix, we kind of make this coordinate mesh into these boxes. So we start out at level 0, which is our entire matrix, and we call this box 1. Let's say our matrix is 400 by 400. And so box 1, whenever you see a 1, that refers to the whole thing, either all the rows or all the columns. Now if we go a level further, we introduce level 1 here with box 2 and box 3, which refer to here indices 1 to 200 and then 201 to 400. And then we can keep going down, and here you would go all the way down to really small matrices, but here I'll just go down 3 levels. And so we have introduced a tree structure. The next slide I give very formally, which means that we can talk about the matrix in terms of these boxes, which we kind of saw here. That's what these labels mean. So when you see A88, that means that it is representing the 8th index set in terms of the rows and the 8th index set of the columns. So what was that? Well, that was just from 1 to 50. And that is exactly what this is. It's 150, 150. Yeah, is there any questions?
So you're saying that the entries in the matrix we're looking at right now, the entries that are in specifically the partition A sub 88,
yeah,
you would access those by going down that hierarchical tree to the place on the tree where box 8 rests.
Exactly.
Okay.
And I love the point, the way you said that, because it's all about using the tree and not all the numbers. And you store all your information about where these boxes are located just within the tree. So you do a lot of operations just within the tree or on very small matrices, and often beyond your initial reading into the matrix, you don't touch the whole thing. You just work with trees and then what are called skeletons, which is what you get from an interpolative decomposition, which we'll talk about a little later. Any other questions at this point?
Where the elements of the matrix are stored? Is stored on the tree nodes, or? So
we don't keep the elements of the matrix beyond the very beginning. Originally you would keep them along the tree. Nowadays, the way this is done is through randomized sampling. So you immediately, your first step is by doing a lot of matrix vector products, and then you just store, the results of those along the tree. So you're already, from the first step, reducing it to linear data. But at least conceptually, yes, you're storing it along the tree. Is that clear?
Not very.
Okay.
You will go on. You will tell us how.
Okay. Anyone else? No. If it's not clear, I should. You make it more clear. Yeah. So the very earliest way this was done was exactly what you said. You would have an array of little submatrices, and you would. You're right. You would have in a tree structure. You would have, at this level of the tree, you would have a box, that represents a 50 by 50 matrix. Mm-hmm. Now, I'm sorry if it confused you, because you're right, it was a convoluted point. I did not need to make it. But I would like to emphasize that, these algorithms are ON not only in time complexity, but also in storage. So we're never storing anything that's actually a full dense square. So
you're reading that dense matrix, and then you somehow, morph them into this structure.
Exactly.
Right, but of course there's a lot of details. So.
There are a lot of details, and I will cover them.
You will touch them, or?
Yes, I will.
Oh, okay.
Yes.
Okay. But you also mentioned random sampling, which is even further down the development.
I unfortunately will not have a lot of time to talk about randomized sampling today, but I would like to say that is the state of the art. That is how in practice it is done these days. You don't touch the matrix elements themselves, you just sample them. Okay, so we have our tree structure. And then, so let's say we want to do a matrix vector product with this matrix. So let's say we want to do AX equals B, and we start just by initializing a vector B just as a 0 vector. And then we just do it basically one block at a time along our tree structure using the same kind of algorithm we thought about in CS515. You can always multiply matrices as blocks. So first we go to just down one level of the tree, and we have A23 and A32 blocks. And we see here I'm going to introduce an idea called children of a node, which are, if we just go back to our tree, the children of 1 are 2 and 3. The children of 2 are 4 and 5. Pretty simple. It's all binary. In the same sense, you can talk about a node's parent, always a single parent, and also ancestors, which are any node that you can get to just by traversing the tree upwards, and descendants, which are any element you can get to just by traversing it downwards. These are 4 very important concepts in tree codes or any rank structured, and there's lots of really fun and useful properties and results that have been shown about how to quickly get and utilize the ancestors, the descendants of a given node for an arbitrary binary tree. So here we have that the children of node 1 are 2 and 3. So then we can just form the part of B corresponding to node 2 and 3 by this simple formula.
The B23 on both the left-hand side and right-hand side?
So this is B23 on the left-hand side. And this is showing how we get it is, so we initialized it with 0, 0. I'm just showing how I would code this.
Oh, it's the assignment here.
Yeah, it's the assignment. Yep, exactly. Okay? So yeah, and then we go down a level and we do the same thing. We go to the children of node 2, are 4 and 5. So we have A54 and A45, and again we form this part of the product in a very similar way. We now, staying at the same level of the tree, we always, in this kind of thing, you hit the level and then you get all the nodes at a level and all the nodes at a level when you do it naively. So now we get the rest of it, and we see that the children of node 3, we saw from our tree, are 6 and 7. And this gives us another part of our B vector. And I won't bore you with all the steps, but you go down to the final level, and the final level, and the final level. And then when we get to the very bottom, it is different, because these are now leaf nodes, which are what you call nodes at the very bottom of the tree. And so that tells us is that now we can get the entire part of that vector. So if we imagine a B vector right here, we now have all the information requisite to get this part of our matrix vector product vector, just by adding the original, the B8 from the previous 3 levels of recursion, and then this times B. And then we do that a few times, and we have our whole matrix vector product, and it was n log n instead of n squared if you would have done it without forming the H matrix. Is this clear so far? Okay, good. Okay, so this is an H matrix. This is, it's a very broad class of matrices. You can't do super fast algorithms with it, but you can do pretty fast algorithms with it. So it was an extremely crucial step in the development. Now I'm going to show something called sequentially semi-separable. Don't worry about it too much, because we're only going to talk about it for a minute and then move on to what's actually used. But there is a very, very key idea here, and that is that of a nested basis. So the definition, we're not going to worry about. But the idea of a sequentially separated semi-separable matrix is that we still have these off-diagonal blocks with rank k, but as we move outside and outside the matrix, we can write each block in terms of the blocks close to the diagonal. It becomes this, so you see at the end, right as far outside the diagonal, it's the product of 4 different matrices, and the previous ones were used kind of close to the diagonal. And it seems like a very restrictive class of matrix, but I'll show in the case of HSS, because that's where it's more useful to us, that actually any matrix where you have, no, I'll wait till we get to HSS. I don't want to be confusing and give a different definition. But yeah, but the key idea here is that we are able to express the matrix in terms of other parts of it. So we don't store nearly as much. And there's not as many parts to it, and just the whole thing is connected, not just these discrete points, discrete blocks that need to be touched upon. And that's what allows us, this was the first one that allowed truly linear time algorithms for SSS matrices, which come up a lot in electrical engineering problems.
So the main difference of H and SSS is that in H the bases are not nested, not necessarily nested. Yeah, they could have no relationship whatsoever. Okay. Where here we assume there's some connection, which happens to happen a lot in applications. Now, if we have an arbitrary H matrix turned into an SSS matrix, we might have to, K, which is my smallest off-diagonal rank, a lot of times K will have to be a little bit higher. But with this, you can get order n, where with algorithms, where with H, a lot of times you have like n log squared n or something. So it's worth it to make K a little bit bigger. So you say it's not trivial to test whether it's disguising. Okay, so these are the issues with SSS. This is why it didn't have a long shelf life. And this is HSS completely resolves these issues. The one is it's not trivial to see whether a matrix is in fact SSS, just knowing it's H. Where HSS matrices, it's a very easy one more criteria to check, and it's HSS, which is the one I'm about to introduce. You're saying check whether an H is HSS is much easier. It's much easier than checking whether an H is SSS. Also, if the name didn't give it away with sequentially semi-separable, you cannot parallelize this at all. And even in 2004 or 5 when they were being developed, they already knew that was going to be a bit of an issue. Where hierarchically semi-separable matrices, HSS, were invented to be parallelized. So that was the huge difference. But it was a very, very important step in terms of the theory and the history to move to the idea of a nested basis. Okay, now I'm going to move
to, I believe, yeah, to HSS, which is the kind that are used in applications all the time nowadays, very, very important, and have very fast algorithms. Okay, so I'm going to first, the definition is pretty complicated, so we're going to build to it in several slides. So first, the idea of block separable, which gets to what we were talking about. How do you know if something's HSS or just H? And it all comes down to the idea of block rows. So is there anything worth here? Okay, so in addition to, in an H matrix, each off-diagonal block has low rank. In HSS matrix, we also require that what we call Hss block rows, which is basically an entire row except for the diagonal. So this is an HSS block, this is an HSS block. Is that kind of clear what I'm talking about? Just concatenating, a whole row except for the diagonal. That must also be low rank. In fact, that must be rank K, whatever that is. And it's often case that this is where we get our K, the off diagonal won't. Now, this seems restrictive, but in more applications than not, if something is H, it will also have this as low rank. These block rows. Yeah.
So try to understand this point. So you're saying suppose this partition you only end up in the leaf nodes where there are 4 blocks.
Yeah.
And then you need to require in the leaf level if you concatenate all for one
in a given row.
Given a row block,
yep.
You just get rid of the diagonal and concatenate all the rest.
That must also have a low rank.
That one to be low rank.
Yes.
But does that you require for other level? I mean, not only the leaf level.
No, that's just at the leaf level. Just the leaf, and that's very important, and also makes it very easy to check.
So for the intermediate level, just require the off diagonal to be low rank. But
yes.
At the leaf level, you
also have to have these block rows. Yes. Yes, and this further constraint is key because this allows us to construct the whole matrix very quickly and to nest the whole thing hierarchically and then parallelize it.
So it means that you will do the bottom up.
Exactly. With an HS. Yep.
You start with a leaf node satisfying this property. All the construction feasible.
Exactly.
Okay.
Exactly, and that is the key here. This allows us to do a bottom-up construction, that is, in bottom-up algorithms. That's exactly the key here. Thank you. So, yeah, and this is very easy to test, this extra criterion, and it happens to come up, H matrices are a bigger class than HSS, that's just true. But in applications, most H matrices turn out to also be HSS, which is very good for us. So here we see an idea. So I call this block separable, which is, the key idea here, we have these block rows, but I haven't recursed. I haven't done multi-levels here. This is just an example of what it would look like at one level. And we see here that the entire row is written in terms of the same basis. We see that the columns of U5 span the column space of this whole submatrix. And if we were to go back to this one, in the same sense, U4 must span the entire column space of this submatrix. And we can do that, for every block row at the leaf level. And that is really the fundamental idea of an HSS matrix. I mean, we use a lot of algorithmic details, but that's really the key that we're able to express that.
Seems that from the expression of A, it seems that you also require this to be true for each column row.
Yes.
For column block, right?
Yes. In general, it's enough to check the rows. But if
the rows satisfy this,
the columns
will be able to have this low rank factorization of the columns.
You're right, but you're right. You would have to have the columns too.
That's interesting. This row implies that. Okay, I have. So it's not intuition.
Okay.
In my mind.
And you actually, to make sure that you're fully comprehending, when you said the intermediate levels must also satisfy it, yes, they do. But if you check at the leaf level, that's sufficient. Okay. So in this single level, what we're really doing is we're writing our matrix A as a block diagonal matrix plus this product of the column basis U, the block column basis for every row, and the basis for all the block columns, times these matrix A tilde, which I'll define in a little bit how we get that. But yeah, and basically the key here is we decomposed it into all very small, and they're dense, but all very, very small blocks that are all nested within each other, and this really helps out to ease computations. So to kind of give an example of why this would be helpful, if this is kind of a variation of the Sherman-Morrison-Woodbury formula on how we would invert a block, not HSS, but basically one level of HSS, because inverting an HSS matrix is actually a lot more complicated algorithm. But if we just have a single level of this, we see that the inverse is just, it can be defined by this operator. I won't read it to bore you. But, and I will quickly, how many do I on time? Yeah, I'll sketch the proof of why we know that this would be valid for this kind of almost HSS matrix. So consider this linear system, which is the same matrix we've started with. We still have these dense diagonal blocks, low rank off diagonal blocks, and we can write each of our block rows in terms of a common basis. Then the key here for this proof is we consider a reduced variable. I call here qi tilde, and we rewrite the equation in terms of that. And basically, we just do a little algebra and consider the shear complement. And what that gives us is that after we eliminate really what's going on at the fine scale, we see that in fact this very simple, almost Woodbury-like formula gives us the inverse. So it is pretty immediate to us. Like I said, this is a kind of a toy example, but that this common block row is just very useful for practical computations. Even if you're not nesting it. But in a second, I'm going to show you how we actually go about nesting it. Yes, Kyle?
Do we think of the A tildes, sorry, I think you already said this. Do we think of the A tildes as basically the SVD diagonal piece?
Yeah.
Okay, cool.
Yeah. That's, in terms of the theory, that's exactly what they are. In practice, we do something a little different. Okay. But that's exactly kind of the idea here.
So we can think of that reduced system as being a 16 by 16, or rather 4 by 4 block, where each block is a diagonal piece? Is that sort of what we're solving there with the reduced system?
Yeah, it'd be...
something like that?
For stability, you wouldn't make it exactly diagonal.
Okay.
But yeah, no, that's exactly the idea here. Okay. Okay. Should I move on? Okay, great. Yeah. So you guys get the basic idea here. When do I talk about nesting it? Okay. So the only ideas left to talk about for basics of HSS are how we nest this in terms of each other, and then kind of how we get to the condensed form, how we compress it. I'll quickly talk about the basic idea, and then in a few slides I'll talk about, in practice, you use something called the Interpol of Decomposition, which I won't have time to get in all the details, but I want to introduce it to you, and feel free to come talk to me if you have any questions about how it's actually coded. So before we do the compression, we just have a dense linear system. And the idea is, relative to our epsilon rank, we want something all in terms of variables in terms of our reduced rank. And Kyle makes a very good point. This is intuitively just an SVD. So I'm trying to, I don't know if I have too much more to say about this without being convoluted. I'll move on to how it's actually done in practice. But here, so assume that can be done. We think about, if we can do this, how much have we actually gained just by writing this row basis? And we see here, we don't quite have linear complexity yet. To get that, we need to recurse what we've done and do multiple levels, where each level we write the row basis, exactly as we were talking about, write the row basis in terms of the row basis at the lower levels. So that's the fundamental idea of an HSS matrix. So what does that look like? Basically, we start, with a, full matrix, dense matrix, broken up into little blocks. We do our compression. We do find the row bases and the column bases at the leaf level. We then, I use the word cluster here, but I think the more correct term, you merge blocks to get to levels where the blocks are twice as big. Then you compress once again. You, by a pretty simple algorithm, you can find the basis is at the second level from the basis at the lower level. You then compress again, you then merge again and compress and merge and compress and merge and compress until you have, for every node in our tree, you have a basis that is all written in terms of your leaf level basis and some intermediary matrices, which are very, very small.
So after compress, you have those diagonal blocks be gray. What do you mean by that?
We're not, when we're compressing, we're not touching the diagonal. Because the diagonal is full rank. We accept that. We're not, we don't try to compress the diagonals. That's why I grade that. Okay, so all diagonals are already compressed. And then when you mean cluster, you're just merge the neighboring. Exactly, you merge at neighbors.
So I mean, at that level, when you compress, you don't touch that diagonal block, and you further compress the, right?
Yes, yes.
Okay, that's the way to go.
Okay, good, very good. Yeah, and so just kind of visually, what we're really doing is we can write, I think this is a good visual. The whole picture is I forgot the plus sign, I apologize for that, but at the very end we have a block diagonal matrix plus, there should be a plus sign right here, a product of all these matrices, where U3 is here the row basis and V3 the column basis for our leaf level. And then we have these intermediary matrices, which give the relationship, how we write that in terms of the leaf level for the upper levels. So basically the whole thing, touching every node of the tree can be written as this finite, very small, just for however many levels of tree you have, product of very special, matrices like this. And so this shows us, in this case, how you would get the inverse, for a multi-level. Of course, it's more complicated when you have more than 3 levels, but. Okay, any questions right now? Okay, all right, I'm about to give now the formal definition of an Hss matrix, which I think we're all ready and on board for. So let me just review the tree structure we're doing. That we have, again, start at the very top level, and each you have children that are in that block. And when we actually do the construction, we're starting at the very leaf level and considering the interactions between a node and all its neighbors, how you can write a parent in terms of its children. And that is the key idea. Okay. So the formal definition of an Hss matrix is that we have, suppose that T is a binary tree. I'll let you read it. But so it's basically everything we've been saying. It's a matrix that you have off-diagonal blocks that satisfy this property, and moreover, you have these Hss block rows that also satisfy the lowering property. And I'm going to introduce a little bit more notation, which is what I call these intermediate matrices. In literature, you will see R's and B's and W's. And that's just showing how can you write an intermediate or a top level in terms of the lower level. And it's by multiplying by these matrices. So these are all, when you read the literature, these are what you'll see. You'll see D's and U's and V's. And basically, if you're talking about a leaf node, D is just the diagonal block. It's very straightforward. It's a dense matrix. And the U's and the V's are just the rows in the column basis that we know we can compute with such a rank. Now let's say we're talking about a parent, something at a next highest level, intermediate, or even at the top. These B's, and I will admit, in the literature, in addition to B's, you will see V's and W's as well. But they show kind of the interactions between the children. And that tells us how we can express the basis for an upper matrix in terms of the leaf level. And the U's and the V's, which we never form explicitly past the leaf level, but they will tell you what would be, theoretically, the basis for some node high up on the tree. Yeah, and the formula to get all these explicitly is actually a little, I think, wouldn't be instructive. It's just kind of complicated. But I mean, this is the main idea. Okay, so what I have left for you, I'm going to spend a minute or two talking about the interpolative decomposition, which is kind of like the how the SVD is done in practice and this kind of thing. But I think first we'll get away from all these formulas, and I'm just going to give you a few examples of the kind of HSS matrices you get in applications to kind of show you that you've already seen these and already have been interacting with these. Maybe just haven't utilized their rank structure as much as you could have been. So I think my favorite example of an HSS matrix is toplets. And the toplets is it's very clearly ON data, right? It's just every diagonal has the same entry. But for the longest time, these matrices, people had a really difficult time figuring out how to get the eigenvalues or how to solve the linear system as in linear time. And even if you were to do a rank decomposition, you would see that this off-diagonal block has rank n over 2. So it doesn't even look like an H matrix. But it turns out you play a little trick and you just do a Fourier transform on either side. And so you look at the toplets matrix in Fourier space. It has beautiful rank structure properties. It is perfectly H and HSS. And because of the nice natures of FFTs and how they preserve eigenvalues and a lot of structure in the matrix, if we look at a transformed toplets matrix, it is HSS, and Gu and Jia proved specifically that the HSS rank is going to be less than the logarithm of the matrix, which makes it useful to us. And so we can do lots of fast. So nowadays, when you see toplets matrices in applications, people will use HSS solvers on them to get either the eigenvalues or to solve linear systems. More straightforward example. Any banded matrix is a toplets matrix. I mean, that's not true. Any banded matrix is an HSS matrix. You can kind of already see that because the any off-diagonal block is going to be rank limited by the bandwidth, and you have a very easy way to nest that basis. They come up all the time in elliptic PDEs as well as geophysics problems, stochastic PDEs. They're very common. In my own research, I see them a lot in medical imaging. Most MRI matrices are actually HSS. So after you do the regularization optimization. So yeah, they're very useful and you get them in linear time. Basically anywhere that you see the low rank property in off diagonals and the low rank property on the HSS block rows.
So for this, I mean, just for curiosity, for this MRI matrices, you have 2D or 3D? 2D or 3D?
We're mostly looking at 2D at this point.
2D. For 3D, I mean, for 3D, the bandwidth is very huge, right? Would that still be low rank? Have you checked?
It's not something I've checked, but that's
for 2D. If I just use the 8 neighboring system, then
yeah,
it could be very low rank.
Absolutely, absolutely. Okay, so yeah, I'm gonna spend the last few minutes talking about the interpolative decomposition, which I think is a very important algorithm because it shows you how are we really. Because I mean, when we do HSS matrices, you're constantly having to compress. And how does one actually compress? Because we're not going to go through the bother of computing tons and tons of full SVDs. And so I'm going to illustrate this through an example. I'm going to take this is just from the Laplace problem, which is HSS. And so yeah, suppose we just have two sets of points. And I like to think of this just in terms of electrostatics. It's the very simple interaction between all these. And we need to compute all these interactions. And we can do that just by forming a matrix. And what we can see is that we don't need to actually look at all the points. And I think I love this example because I think it kind of gets at, it's very visual. And it gets at what you're doing anytime you do an interpolative decomposition with an HSS matrix. You're kind of getting this little skeleton of the points that still gives you all the information you need to solve the problem to very high precision, actually arbitrarily high precision. You have a question?
So you mean skeleton points mean the cluster centers, or what do you mean by skeleton?
Skeleton points mean, we can see, like for instance, this example, if we do the interpolative decomposition, which is what I'm about to explain, it will tell us we only need to keep these points, and we still get all the information of the cluster.
I mean, if I look from the target location. So I mean, are you talking about you want to consider the interaction between the red and the blue?
In this case, that's what we're doing. That's this problem. But I mean, you can, like I said, it can be any Hss matrix, and you're kind of doing the analog of this. I just thought this was a nice visual example of what we're doing when we take an ID. Okay, so again, what is the theoretical best factorization? And I already told you, it's the SVD in theory is the way to do this. And here we have the theorem that gives us this. Eckert-Young tells us in terms of the, in terms of whatever norm you use, the SVD is going to give you the best way to do it. But in practice, we don't want to use the SVD. And there's a few reasons for that. The big one, at least until very recently, is just not feasible computationally. Fast SVD algorithms are hard, and especially in an Hss matrix, you don't know exactly what structure all your generator is going to have. But I think more pertinently, the factors in your SVD depend a lot on the geometry of the physical problem, and it's just not something you want to mess with. I mean, basically, you would have to custom build all your translation operators every time you did it. And seeing as you're relying on this at every step of your tree, this wouldn't be a way to do it. So we do something a little different. It's called the, like I said, the Interpol of Decomposition. So what this is we decompose a matrix in terms of a skeleton times an identity matrix. And one thing we keep in mind is that no entry in V has magnitude greater than 1. So that means it's well conditioned, which is very important to us as we're using these over and over in our computations. Now, that would be nice in theory, but people had they knew this in theory this would work, and it would be a great way to kind of get this cheaply, but they had a really hard time kind of implementing it. And until a really nice result back in '96 by Mingu, my grand advisor, and Stanley Eisenstadt, my great grand advisor, showed that if we relax this condition from 1 to 1.1, it's just as good in practice, and it's a lot easier to meet this condition. So basically, we just do more or less a rank revealing QR, the kind of thing you've seen a lot in CS 515, but you do it with lots of randomized sampling and tricks to get at linear complexity. But basically, you just do that through Gram-Schmidt or reflections or anything, and you can do this in linear complexity, get this skeleton that satisfies your 1.1 criteria, and we have what is almost as good as an SVD. And I will show that it's, in a few slides, it's actually arbitrarily as good as an SVD. So kind of to illustrate what I'm doing here, so in the case of this the Laplace problem, we show that exactly as you're saying, in terms of viewing it from the target, these are the only source locations we actually need to keep, and we resolve to 10 to the negative 12, 10 to the negative 13, all the data there. In terms of linear algebra, you can just think of it in terms of doing a Gram-Schmidt. And you're just doing a rank revealing factorization that shows you exactly what you need to keep in terms of resolving the data. So, and here I show that the nodes marked in red above are the nodes marked by the index vector I, which shows exactly what we need to keep.
So I have a question.
Yeah.
So here you're saying if you relax the magnitude of elements in V,
yeah,
then but suppose I have a matrix A of exact rank K. I first do rank revealing QR, so I know which are the K columns I can pick.
Yes.
Right? I just pick them, and then I can compute the V based on the.
If you have a matrix of exact rank, you probably wouldn't need to play tricks with relaxing the parameters. Those turn out a lot nicer. But this would be more for something that's like decays really fast, but the singular values stay non-zero, is when you would need to do something like this.
I mean, I just try to understand how do they do the ID. So you have A, and then you do rank revealing QR.
Yes.
To identify the K largest columns you want to keep.
Of your block rows. Right. You're doing rank revealing QR on the block rows.
Right.
And that shows you it shows you what you need to keep, exactly.
And then you compute the V based on.
Exactly.
So it's basically we still need to do a rank revealing QR for ID. Is that right? Is my understanding correct?
You do need to do a rank revealing QR, but with a rank revealing QR, unlike an SVD, there's ways to really speed it up with randomized sampling to get linear complexity.
I don't know that. I mean.
So this is better for us, but you're right. You still need to do an RRQR.
Okay.
Yep.
Sometimes that's still very expensive unless you tell me how to do the random sampling.
Okay.
That's something I don't have.
Okay. Okay. Very good. So I just have just a minute. Yes, and this is just the other. Now we're doing Gram-Schmidt and the rows, and now this is, basically in this example, like the target locations and source locations just show the information from the rows and the columns, is what's going on physically here. And so now we have skeletonized both the source and the target. So this would, for any arbitrary Hss matrix, this would just correspond to the full skeleton, both for the rows and the columns. And this is what I wanted to get to. So the SVD, if you do this, is the best. It will always be the best. That is a theorem. You want the best possible result with 20 terms, it's the SVD. We can't beat that with an ID. But it is really, really close, and we can do the ID in linear time. You compare to something like a fast multiple, like a multiple expansion, which isn't a totally fair comparison for a number of reasons, but you see how much more gradually that tapers off.
So this is for this log potential function.
Yeah.
Or I'm curious to know. This is very nice. Is there any hard potential function? The decay is not of the.
Yeah. Helmholtz isn't particularly well behaved.
The exponential or you mean Helmholtz operator?
Helmholtz operator in 3 dimensions is not particularly well behaved in terms of how well it decays, but in a lot of cases it is. And basically for anything with HSS properties, you're going to get really nice decay like this. So yeah. Okay, so I'm out of time for today, it looks like, but I will come back next week. And the one thing I didn't get to was how we construct these Hss matrices. So if you guys want to hear about that, I can talk about that next week. I don't think it's particularly instructive. There's lots of great software out there that just does it for you. What I would really, but I'd be happy to talk about it if you want me to next week. What I would like to focus on is talking about how we can do really fast solvers for Hss matrices, whether they're sparse or dense or symmetric or non-symmetric. As long as they have these Hss properties, we can get linear time solvers. And the week afterward, the part I'm most excited about, because this is my research, is, again, regardless of whether you're looking for all eigenvalues, some of the eigenvalues, symmetric, what have you, you can get all of them in linear complexity if it's HSS. All right, thanks guys.